When we observe the motion of an object moving at constant velocity, we can understand the physics principles happening and how the object is moving. In this case, we will be studying a tennis ball rolling across a floor. By analyzing this example, we can come to the understanding of constant velocity and how it is affected by physics principles. We can start our analysis of the physics principles happening on an object moving at constant velocity by capturing the motion of this object via camera. When a tennis ball is rolling across the floor, we can analyze it using position and time. Upon capturing the object moving, we will also be recording the time it takes for the object to move and how far it moves. After doing this, we know that the physical principles included in analyzing this include Newton's first and second law, which state that an object moving in motion will stay in motion unless acted upon by another force, and Newton's second law, which is the fact that force is equal to mass times acceleration, or in this case, when there's no acceleration or constant velocity, net force is equal to 0. In addition, we'll be studying velocity, which is the change in position over the change in time, as well as the velocity and position update formulas. The experiment that we will be recording is the object traveling at constant velocity or the tennis ball rolling across the floor. After pushing the ball, we will wait for the ball to reach velocity and then we will record it for a certain amount of time. We will then put this ball into tracker to find its position. And then we will create a computational model in GlowScript code to describe these observations. With this computational model, we will predict what the ball will do upon motion, and then with tracker, we will observe what the ball does in a lab setting. After doing this, we'll find the results of the tennis ball rolling across the floor. So to go deeper and understand the computational model, we will take the GlowScript sample code provided by the professor, and then we will enter these initial conditions. We will set the initial position and velocity vectors to respectively 0.362 meters and 0.6 meters per second. We have found these by recording the object moving in tracker and then taking its set initial position and then the average velocity taken from the first two frames. Next, we will set the net force equals to 0 thanks to the Newton's second law. Next, we will add the velocity and position update formulas to the while loop. Upon doing this, we will then be able to project and predict what will happen as the object moves at constant velocity. After we analyze the model of the predicted position versus time, we can see that position will change 0.582 meters in 0.970 seconds, and we will have a constant velocity of 0.60 meters per second. However, this isn't exactly what happened in the observed lab. We can watch what happens in the observed lab here, and it reveals what the object looks like as it rolls in constant velocity. Now, as we see in the graph on the left, the observed position versus time isn't exactly the predicted position versus time, where the position observed changed 0.471 meters and the time passed of 0.983 seconds, to have a velocity constant of 0.480 meters per second. So when we put these two together, we can better see what it looks like with the model and the tracker. The computational model, which is pictured in red, is a straight shot down with a constant velocity. However, the tracker, which is placed in yellow, isn't exactly the same. While it starts off with a constant velocity, it appears to slow down. So why do the model and observational data differ? One of the reasons is due to human error. I found the ball's constant velocity and displacement measurement based on tracker, which is only an estimation of how far it actually moved across the screen and the velocity which was taken as time steps. However, observationally, it wasn't actually a completely constant velocity. It was only close to it. The only way we can improve this is by the computational model is to take averages of the instantaneous velocity throughout the observation rather than only the first step. Also, I can try to record and reach a constant velocity within the object with multiple trials. Now, if we flipped the axis when measuring and tabulating the data into a graph, the magnitudes of the values would stay the same. However, it would be in a positive format rather than a negative, and it would look similar to the graph posted here. So what does this mean? This means that as the ball is moving at constant velocity, it has zero net force. It has a push and pull of normal and gravitational force, keeping it at zero net force. The velocity is a change in displacement over the time, meaning that this constant velocity can be found by looking at how far it moves during a change in time.